we're going to do right now today is obtain the second solution using the Wronski method. Okay, that's the first thing we'll do. And then we'll talk about if P of z and Q of z at z equal to z naught or z equal to 0, if they're not well defined, and also z times, but z times Q of z or z squared times Q of z exists, how to propose solution, Frobenius series solution, generalized power series solution method. We'll talk about these two things today. Okay. All right. So what we saw last time is the following: that for two solutions to be linearly independent, we must have this condition, Wronski. Determinant of y1 is the first solution of the second order differential equation. This is the second solution to the first derivative. Okay, this should be non-zero. That's what we saw, right? So for any I've written the second order differential equation in a canonical form like that. This should be non-zero for if y1 and y2 are linearly independent. So wx is nothing but y1x, this much we know. We'll just take the derivative, the expanded determinant. That's the definition of a Wronski. So the first thing is what we're trying to do is obtain the second solution of the second order differential equation. That's what we're trying to do. So all this any general second order differential, that's the definition of Wronski, and that's a condition for y1 and y2 to be linearly independent. And so we start with that. These are things that we already know. All right. So what we're going to do is divide the Wronski by y1 squared. Okay, let's see what happens to that. So divide the whole equation by y1 squared. What do we have? So that gives you what? y1, y2 prime x, y1 squared x minus y2 x, y prime x, y1 squared x. So all I've done is so that is nothing but y2 prime x over y1 x minus y2 x. We have no simplification there. This is what we get. The right-hand side here, okay, if I want to write this as a whole differential of some quantity, what would that be? Can we write it like that? I want to write the right-hand side of that equation as follows: several functions of x. Just guess. what function should I put in the square parenthesis? There's a lot of clues there because you can look at the first term and, you know, at least that's giving you a little bit hint. Y2 over? Is this what? Does it give you that? Take the derivative with respect to the first term, that would be that, the other term like that, okay? And then you're taking the derivative with respect to the denominator, which will be negative y1 square x times the derivative of that. Okay, so this will satisfy, this function will satisfy that. So once you get this form, then I have a relationship. Okay, I have something now. Okay, so what I want to do is, given knowing y1x, how am I going to predict y2x? Okay, so what do I do with this equation now? You know, assuming that we know how to calculate Wronskian, but how are you going to get y2x in terms of y1x? What can we do? What kind of manipulation can we do with that equation? My goal is to get y2 in terms of y1. And I have a differential sitting there. But I want to extract y2x. So our goal is to get y2x, knowing y1x. How am I going to get that? Yeah. Integrate both sides, right? So if you integrated both sides with respect to x, you will get what you will have is, I'm going to look at the other side first, because y2x over y1x is then equal to nothing but variable, right? So I'm just changing that to. So this constant, you know, we can have 0 or any constant, doesn't matter. A constant time a solution is always a solution. So we have now a formula which says y2x, the second solution is nothing but the first solution, okay, times this quantity, integral of the Wronskian divided by the first solution, which you already know, and the subsequent function of x, right? You know all of them. So here you can put, most of the time you'll take it as 0, but it could be any constant. But when you you integrate and differentiate, if I have a constant, doesn't matter, right? Differential of a constant is 0, so I can always add to the solution. Such a solution always a constant. Okay. So because of that, we don't specify. But in most of the practical problems, you put it as 0. Doesn't matter, even if it was a C or something, doesn't matter. Okay, I mean, because the solution is like constant. Right? Whatever you integrate, that will be constant. Okay, constant times the solution will be a solution anyway of the original solution. So this is how you generally express the solution. But what it means is you can put any constant, not necessarily 0. Okay, maybe, but that's what you use in the
so the x there means that you're going over the whole available domain.
Which x? This?
The x in the integrand. It means you're going over for all valid values of x.
Right. It depends on, the domain in which you're solving eventually, right? But right now it's a variable here. But this, you could be in principle be solving this equation in certain domain or whatever, right? And it's also possible. Right now we are putting as a this experiment is the only thing which goes from 0 to x. Okay, and x could be whatever in the domain that you may be solving this equation eventually. So this is a useful thing, provided, as I said, I can get a good, nice expression for Wronskian too, because if I knew only this formula, it's useless, because I don't know the second solution or a derivative, I cannot calculate using that formula. So we need to have other tricks to find out how, for a given differential equation, can I get another expression for Wronskian, which will be useful to calculate a second solution. Okay, so we get to that now. So I'm going to write the result first and then we'll prove that. So Wronskian, as I said, I think I wrote last time, we could write it as, if I know the second order differential equation, if I'm putting in the canonical form, and I know the derivative of y prime, that's all I have to know to calculate Wronskian. Okay. So this is given as, again, this is function of x, so this integral goes to that, and we're going to call this x prime, this is a dummy variable, and this is 0 to x or whatever, and you can have a constant here again if you want. So that constant, we again take it as 1, okay, for most purposes. So this is the formula for that, Wronskian, under expression for Wronskian, and we will use that because, then we can integrate this expression. So let's see where is that formula coming from. So you should know both forms of the Wronskian. So this is the formula that I know originally, right? I mean, from a known thing, we are going to get another expression. Take the first derivative of this expression. Respect to x, so I'm just going to write w prime. That is y1 prime, y2 prime, plus y1, y2 double prime, minus y2 prime, y1 prime, minus y2, y1 double prime. All right? So these terms are repeating, so I can cancel that. So what I have is w prime is y1, y2 double prime, minus y2, y1 double prime. That's what we get. So if y2 is a solution of this differential equation, I can write w prime as y1 times px, y2 prime plus qx, y2, right? Minus y2, second derivative with respect to, that's the first solution. So the first solution is to satisfy my original differential equation, right? So dx y1 prime plus qx y1. Okay, so So all I've done is substitute for y2 prime and y1 double prime from our differential equation. Let's see where, sorry, what it is, y1, sorry, I'm just making a mistake. Y2 prime is, so y1 times that, right, which is minus px, y2 minus qx. So all I'm doing is substitute for y2 double prime, okay, so y1 times minus px, y2 prime minus qx. Similarly, I have to write here y2, y1 double prime, substituting for y1, yeah. So that is minus px, p y1 prime minus qx y1. So this is my second, this is my y2 double prime, and this is, that's all I've done. All right. Can we get anything eliminated? This is what, minus p, the second term is what, minus qx y1 y2, and that term is what, plus qx q1 q2. So we can eliminate that. So we have first derivative of the Wronskian is nothing but minus px y1 y2 prime, right? And then this is what, plus px, right? That is plus px y1 prime y2. So I could, in principle, write this as minus px y1 y2 prime minus y2 y1 prime. Okay, that's what we have. The first derivative Wronskian turns out to be this. So let me write this out like this: dw over dx is what's the stuff within the parentheses, the square brackets. What is this quantity? That's Wronskian? Yeah. Right. So, like this. So I can now, put all these W variables in one location. Take it one side. Now can we get an expression for W? Same thing, like integrate both sides, okay? Integrate this side with respect to W, the other one with respect to so I can write this as natural log of W is nothing but that quantity. Again, we always have constants available, like, I can put a natural log, I don't have to put C, actually I can put natural log of C too, which is also constant. So, in principle, you can have W is nothing but, these are the main terms you have. I can put a C here. And, this you can choose again, whatever constant you want, but generally we put 0, okay? Then you use 0, but you can put anything. Right. So, yeah, so we have now a neat expression for a neat way of calculating a second solution, which only exploited the fact the solutions have to be linearly independent. That's it, right? And that's all it did, right? square of the first solution. Alright? With W given by that formula. So all you have to remember is to put the what a given differential equation in the canonical form to get the correct expression for P of P, right? I mean, you know, if the coefficient of second derivative is not 1, we have to divide the expression through that. All right. So let's just check the formula from the case that you already know the solution, making sure this is really the formula. So what is P of x here? P of x is 0 and Q of x is 1, right? So my Wronskian here is, we'll take the C as 1, right? Minus of 0, whatever it is 1, right? So Wronskian is 1, it's a constant. You can put a C if you want, but it's a constant. You can put 1 C, whatever. So we know that one of the solutions would be sin x, right? I mean, so we have to predict y to x is cosine x through that formula that this is correct, right? That's what we're trying to do. So y2 of x is the sine of x you can put that as a constant, so y equal to 1. And then here we have what? Sine square of x prime, right? Which is cosecant square of x. And what is integral cosecant square x? Remember integral of secant square x? So just from there you can try to, I'm just trying to see, if you remember that you can. Huh?
Natural log of secant x plus secant x.
No,
Differential tan is 6 there.
secant, yeah, so the other way, yeah. Now here's that.
That's
So differential of cotangent x is cosecant square x. So this is nothing but cotangent x, cot x. So that's cos x over sin x. I think I guessed it because we know the solution. What could have been that? But y2 x is nothing but cos. This is cosine over sine, right? This is equal to cosine x. Which we had proved last time through the ordinary power series method. We got both solution through that method, right? Now we are trying to get it by a different method. And this is useful only, as I said, I mean, only if I can write my first solution in a closed form, in an analytical form. If you left it in that series, full series, because we are using power series, solution will be in series form. So you have to identify that series to a function, then you can use that method. Otherwise, it's going to be difficult, right? So that's why you have to know always how to go from series to function, function to series. of some at least common thing. Vector. Goes by the name, the person who discovered that, this method. So whenever, let's start with this, So what we saw was if P of Z and Q of Z last time is analytic at Z equal to 0, we automatically can get to, we can use ordinary power series as the solution, okay? And both Y1 and Y2 will come with that method. On the other hand, what I said was if P of Z at, one of them, either this or Q of Z, this or tends to infinity, okay? One of these terms. If we can check the other condition that Z times, although that is blowing up, if I multiply Z times P of Z, this becomes, it's finite, it doesn't blow up. Similarly, Z squared times Q of Z as Z tends to 0 or Z tends to Z naught, wherever your point of expansion is finite. Okay, let me okay, I'm going to put this in there. So this is a point of expansion of this power series. Okay, if that is finite, then we can give a generalized power series solution. Okay, so the independent variable here is Z, is d squared y or dz squared, because P is a function of Z. Okay, so remember that. So basically, maybe I can, because there was confusion yesterday when I talked about essential singularity, I just want to say what it really means is P of Z at the most has a pole of, what we call a simple pole. It is only in a function form like 1 over Z. Okay, it's not, if P of Z is like 1 over Z squared, we call it as a, it's a pole of order 2. Okay? If it's like 1 over Z cube, we call this pole of order 3 and all that. Essential singularity is something you cannot remove it at all, okay, for that function, okay, because if it is a, generally I can remove it, but the series solution is possible only if it has a simple pole. P of Z has a simple pole. Q of Z has a pole of order 2 at the most. Okay? It cannot have a higher order pole. That's all it means, okay. So that's why, what if it's pole of order 2, you're able to remove it by multiplying by Z squared. And it becomes regularized after that, right? So I just want you to be clear that if this condition is satisfied, what we call as Fuchs condition is satisfied, then I can propose a solution of this form. This is what is called as Frobenius series. I'll write it like this. So last time we didn't have this term. We had only infinite power series of this form. And all we had to do was find out the coefficients, a sub n, the quotient relationship, and find the coefficient. Sigma here is called as initial roots, and our goal is to find not only set up the recursion relationship, and we set up what's called as initial root equation to find out sigma. So once you can determine sigma and a sub n, we can find the solution of a differential equation of this form, where P of z and Q of z are not analytic at z equal to 0, but it satisfies Fuchs condition. Okay. Then we can propose a power series solution, which is a generalized power series, a Frobenius series. Series as solution. That's what Fuchs did. This is Fuchs' work, okay, all these things, okay. Here we'll come up with several cases. I will talk about it in detail. You know, we will set up the initial root equation, and it so happens, if it happens, okay, maybe I'll tell you what it is, and then maybe discuss it. You know, if the initial roots are distinct, and you know, the difference between the two roots, sigma 1 and sigma 2, if it's not an integer, we can get both solutions by the power series method. If the initial root is such, they're identical, of course, you're getting only one solution from this equation. So we have to have other methods to find the second solution, not only non-scaling, but the other methods too. And if sigma 1 minus sigma 2 turns out to be an integer, we use the larger of the root to find the first solution. The second solution, the second root, may or may not lead to an independent solution. We have to check that. Okay, so there are different cases also once we set up the initial root equation. Okay, so let me just go through that a little bit more carefully. Where all these things come from. All right, let me keep this. All right, so what we know is P of z is not analytic, but z times P of z is analytic, right? It doesn't blow up. So what does it mean? Any function which is analytic, what can you do with it? That's the starting point for what I'm going to do and to get the initial roots. So I just want you to understand this. If a function is analytic, do you know how to write it in another way? I mean, we will also always, in physics, a function, we write it in different forms, like the series form, or Fourier series form, or Fourier transform. Yeah, we represent function in different forms, right? But if a function is analytic, okay, like here z of p, z is some function, okay? If that function is analytic, what can I do with it? What are the different series that you know, I mean, you have come across thus far in your math class? Or just you know, Taylor series. I mean, that's simple. You know, your derivatives exist, and now the function exists, the derivatives, you know, all that higher derivatives exist, right? That's the definition. That's the definition of a function being analytic, okay? So I want you to understand the meaning when I say analytic and all that. Okay, so let me call this function at this point product of that, and that is analytic. Okay. If that is analytic, surely I can write it as what? Some coefficient. I'm expanding about z equal to 0. Okay, z minus z naught, z naught is 0. Okay, and similarly, I can write another function t of z, which is z squared times q of z. I can write it expanded to Taylor expansion. Okay, because this guy is analytic. Del B. By analytic, that's what we mean. The function is del B. All right. So I go back to this equation and I'm going to write my y double prime as s of z over z, okay, y prime, and q of z as d of z over z squared times y. You see, all I've done is substitute for p of z in terms of all this, okay? And y, if this Frobenius series solution exists, is of this form, right? I mean, an, I put the sigma inside now. I wrote that initially, so I wanted you to see the difference. You know, we had only that series and we had one term extra. So I'm going to write it like this from now onwards. So I can calculate y prime and y double prime, and then see what happens. Right? So I'm going to substitute all this, the Frobenius series solution thing here, n plus sigma minus 1, a sub n plus s of z over z, y prime is there, n plus sigma an z n plus sigma minus 1, n going from 0 to infinity. Alright. So s of z y prime I've written down. Okay, and plus q of z. Q of z is that, so t of z over z square. Okay, y is 0 n plus sigma equal to 0. Alright. Alright, so let us a little bit simplify this. This one is what? This has becomes, z is in the denominator, right? So this has becomes z plus n plus sigma minus 2. I'm going to take this up. Okay, so I'm modifying this to minus 2. Okay, and similarly I'm going to take the one in the denominator up, making it that. Alright, the summation is over n, okay? So this is nothing but z to the power of n times z to the power of sigma minus 2, right? I mean, that's what that is. So I can factorize z to the power of sigma minus 2 out from all these terms. So we got all that, I can take it out. Okay. So if I took that out, what I get is the following. Summation a sub n, n plus sigma, n plus sigma minus 1, z to the power of n, n going from 0 to infinity, plus s of z, a sub n, n plus sigma, right, plus a sub n T of Z. Let me Z to N. Alright. That's right. I took that N plus sigma minus like that. S of Z. An is N plus sigma. Okay, An T of Z. Okay, fine. Alright. So my goal here as why am I doing this? Okay. You know how to calculate A sub n. I gave a recipe for that, right? You just set up all these things, you have to find a recursion relationship, whatever it is. But I need to find a way to calculate sigma. Okay. I mean, this is all I have. I have this equation, and all I have to do is substitute the solution. And how can I come up with a way to get a solution? Okay. So what we looked at is look at this equation. We are going to examine this equation for just n equal to 0 and z equal to 0. What happens to it? Okay, oh, important thing, I forgot to say this. This is also very different from Frobenius, the ordinary part series. This is a solution we propose when P of Z and Q of Z is not analytic but satisfies Fuchs condition. The first coefficient here should not be 0. Okay. That was not the, in the ordinary part series, you could have A naught to be 0, A1, if remember we could have it. Okay, that condition was not there. This is also a requirement here. Okay, so let me come back and mention that. When you look at it, I remember why it should be there. So when n equal to 0, what happens here? We have A0, right? We have sigma minus 1. Okay, n equal to 0 equals 0, 1. Okay, so I don't have to worry about that. And I have A0, S of 0, sigma, okay? A0, T of 0, and what else I have? No, right? So I really could write, this equation is nothing but, I can write A0 out, it's common. I get an algebraic equation in sigma. Okay, so the simple algebraic equation sigma, second order, which I can solve. If this condition, if A0 is not 0, it is this quantity which has to be 0. We know how to calculate S of Z and T of Z because if you know the differential equation, you know P of Z and Q of Z. So you have to calculate these quantities for Z equal to 0. So you know how to calculate that. So you can evaluate sigma 1. It's the second order differential, so we'll have two roots, sigma 1 and sigma 2. Okay, so we will calculate that. So this is the equation which is called as initial equation. So in this case, you have to set up an initial equation. And solve for sigma, the roots, okay? And of course, we'll also set up recursion relationship that is obtained by looking at coefficient of z to power n or something like that, 1 power, and then you can get relationship with an and an plus 1 or an plus 2 and all that. So if you do that, for Frobenius series, you not only have to calculate that to get the roots, and you'll also have to set up the recursion relationship to calculate the coefficients a sub n. So that we'll do for specific problems, right? I mean, so to calculate the ANs and just you know what it is. All right. And once we have that, you can calculate it, okay? So now there are different cases, okay, depending on the two roots, sigma 1 and sigma 2. So we have several cases whether this series solution, which is a Frobenius series, whether it can lead to independent solution or not. The difference between the two roots, if it's not an integer, whatever solution get from this, if it's not an integer, then both solutions y1, in this case z, right? Y1z and y2z are possible from the series method. Okay, so this is, you may have an identical solution, of course one solution, that's obvious case, right? Only one solution possible. Case 3 is sigma 1 minus sigma 2. The difference between the two roots is an integer. If the difference between the two roots is an integer, typically only the larger root will give the solution, sparse seed solution. Larger root is chosen. Larger initial root is chosen. You may not necessarily give an independent solution. Okay. Okay, sigma 1 is 3/4. Sigma 2 is 1/4. Let's say I got some differential equation. This guy, sigma here, can be real or complex, okay? I mean, it could be complex number or real number. I just want to add one more thing because of adding more things and remember other things I can tell you. So in this case, do we have both solutions from our series method?
For the first case, no.
No, right, I mean, And which one will you take to find the solution? The first one, larger one, right, at positive sign. Sigma to the power of half, that's the one which will lead to your series solution. Okay. The second one, both are possible. So because the difference is, it's not an integer, both are possible. What about the third case? We'll do an actual example where we'll see the series breaking. Even if you try to do it, you can't get the solution. Something will happen. Representation, break and all that. The third case, what is sigma 2 minus sigma 1 star? Can you So we have to find out what this quantity, right? Sigma 1 minus sigma 2, right? So we have to evaluate this. Sigma 1 minus sigma 2 is what? Sigma star, right? What is this quantity? This difference, what is it?
Would be 2 times the complexity.
So this can be written as real plus imaginary part of it, right? Real plus imaginary part of sigma. Okay. And so you have similarly real part of sigma minus 1. Sigma 1. So you have to take the complex of it. So you have minus I imaginary part of sigma 1, right? So the real part will cancel. So you have, this is nothing but 2I times imaginary part of sigma 1, right? Which is not 0 and it's not an integer quantity. So both solutions are possible. If you have such a situation, both solutions are possible by Poisson method. So that's why we need to have other methods because there may be situation it's not possible to find a second solution of part series at all. So there are polynomial methods, derivative method, in addition to Wronskian method. There are other methods to find solutions to obtain a second solution. All right, is this clear up to this point? So I can proceed with the example.
So to be clear, the integer part is only for real numbers. So saying does not equal to integer, we mean real integers.
What did you say?
The integers only belongs to real, so like 5I, not an integer.
Yeah. And also, exactly. Yeah. See, what I want to emphasize is, don't get fooled by if it's a rational number here, automatically, the other one is rational, automatically you can get both solutions. Now, is the difference between the roots which have to be an integer. That is, I mean, if sigma 1 is integer, 2 minus 1, whatever it is, then you know automatically. But it is cases like this, you may get fooled, think I'm going to get both solutions by power series method, right? I mean, which is not the case. I mean, although individually they are not integer, the difference between what we have to look at is the difference between the two roots. Okay, that has to be an integer, not individually they were rational. That but it's not going to lead to two independent solutions in that case. think that's the main. All right, let's do an example so that we understand how to use the methodology and what's it like? Yeah, okay. All right, so this is a differential equation we want to solve. So what is P of Z? Everything, let's write it clearly. What is P of Z?
3Z over Z minus 1.
Yeah, let's write down here so that we can, I just spaced out something else. P of Z is 3Z over Z times Z minus 1, right? Q of Z is 1 over Z minus 1. So at Z equal to 0 is P of Z analytic. And we are going to expand around 0, okay, Z minus in the power series, okay, the expansion point is 0. So P of Z, what is P of Z? At Z equal to 0. 0, so it's fine, it's not going up. What about Q of Z? That's blowing up. So even one of them blows up, we have to, do the Frobenius method, right? And but Z times P of Z, which we need definitely, right? I mean, Z times P of, because we have to calculate all that stuff, is what we called as Z, S of Z, right? So that is nothing but 3Z over Z minus 1. Z squared times Q of Z, which we call as T of Z, is Z over Z minus 1. And we want to look at the behavior. So we are looking at the first look at behavior of P of Z at behavior of, basically when I say behavior, analytical behavior of P of Z, Q of Z at Z equal to 0. That's the first step. Okay, they're good. Both of them finite, go with the ordinary series part. Not this one, ordinary part series. But even one of them blows up, then you go with the Frobenius series. All right. Now this is what this is. So what is S of 0? S of 0, because I need to calculate the initial roots. What is that? 0, right? T of Z 0 is also 0, right? So my initial roots are what? Sigma times, this is my, that's what happens, right? In this case, for this differential equation. So this is sigma 1, let me call the higher root as sigma 1. Sigma 1 equal to 0, sigma 2 is 0. Okay, so I'm always going to call the first root as sigma 1. Alright? Alright, so if you don't remember that formula, I mean, you may remember, you may not remember it. The way to get the initial root is you have to remember definitely what the bar series is, y prime, y double prime, you can do it, right? Always look at the differential equation, what do they do, the expansions, or plug that into the differential equation, and look at n equal to 0 and z equal to 0 term. That's how we got it. So you don't, if you forget it, you still can get the initial equation, okay? You go back to that and, look at n equal to 0 and z equal to 0 term, and that will lead to your differential equation, okay? I mean, the initial equation, in order to get the roots. All right, so what is sigma 1 minus sigma 2? Is an integer, right? The difference is an integer, so I can get only one solution for this method, Frobenius method. So I put this sigma 1, put sigma 1 at towards end, after I do all this, after I set up the recursion relation, I do that, not initially. Sorry, I do have root as one. All right, now go back to this equation, and I erased all of them, so get them all back. Y prime is n plus sigma an. Y double prime is n plus sigma minus 1 a sub n. All right, so let us set up now the recursion relationship. That's what we are trying to do. We are going to do that. Y double prime is simply n plus sigma minus 1. Plus 3z y prime is a sub n plus sigma z equal n plus sigma minus 1 plus an z equal n plus sigma, all that should be equal to 0. All right, so we have to, there are two terms in the first term, right? Two powers of different powers will come. So we have to collect similar powers, so let us get that going first. The first term would be n plus sigma minus 1. And this will be z squared, so I can get rid of that. It becomes z equal n plus sigma. Then I have minus z, right? So that will be minus a sub n. What is it? Minus z, that's what we do, right? Z squared minus z, n plus sigma, n plus sigma minus 1. Z times that, I can reduce that power by 1, I think. Then I have plus 3 times a sub n, n plus sigma, z z to the power of n plus sigma, that z can be pulled inside, right? So that will be that term. Then I have one more term which is an z to the power of n plus sigma, n going from 0 to infinity is equal to 0. So at least we have two different powers here, so we can, we can sort of take care of this. Leave that. Okay, let's see if I can. Can you check everything's fine before I erase? Because I'm plus minus negative sign 0 plus 3 times that. That's fine. Alright, move this also in this space. Alright, so I can combine all these terms, and so what I have is a sub n, n plus sigma minus 1. Then I have plus 3 n plus sigma, right? That is 3 times plus 1, right? So what this? Let's check the plus. So this is all z to the power of n plus sigma term. And that is equal to, so a sub n plus sigma, n plus sigma minus 1, z to the power of n plus sigma minus 1. Z to the power of sigma is almost, we can pull it out at the summation, okay, right, because they are common everywhere. So I want to compare the same power. Let us say you want to compare, you can even go either way. You can change, you want to compare the power of Zn or z to the power of n minus 1, when both sides in one will be, yeah, I have to change any of them here. Let's compare the power of z to the power of n both sides, okay? Compare the power of, I have to change only one term, right? Power of z to the power of n on both sides. So I've just pulled z to the power of sigma out, okay? I mean, we can pull that out, okay? That, because that's common, so this is what I'm trying to do. Look at that. Term. Z to the power of n. So I have to do that, in this case, I have to change n to n plus 1 only on this side, right? So I will have the following recursion relationship. So we can simplify this n plus sigma whole square minus, then become, so this becomes what? This can be simplified nicely. This is n plus sigma square minus 3n minus 1 plus, so this is 2 times n plus sigma and plus 1. So this looks like a square plus b square plus 2ab, right? So this can be, this is nothing but n plus sigma plus 1 square, right? A square plus b square plus 2 times ab. So this whole term here could be written as n plus sigma plus 1 square. Is this clear? All I did, this is n plus sigma square, this is minus n plus sigma, this is 3 times n plus sigma, I can cancel, okay? So if you expand this, this is what you should get. So what I have is the following recursion relationship. A sub n plus sigma plus 1 squared So I pulled z to the power of sigma everywhere out, okay? That's what I had done, that's why, that's not there. But if you want, you can compare the power of z to the power n plus sigma plus 1, and n plus sigma minus 1, those terms you can compare, but we don't need it. So this one, I need to change, that is that, and this one we have to change to a sub n plus 1, okay, in order to get the recursion relationship. N should become n plus 1 everywhere. So that will be n plus sigma plus 1, the first term, and this becomes n plus 1. So this is nothing but n plus sigma, right? That one will cancel with that. So that is n plus sigma. Is this clear? So now this is the power of z to both sides now, in both cases. This is the coefficient, we're looking at the power of n, right? So coefficient of compare the coefficients of z to the power n on both sides. So that's what we do. There's no summation. I'm just looking at one term, right? So now we have a very nice expression. We have an, okay, let's say an plus 1 over an, if we want to do that, is nothing but n plus sigma plus 1 divided by n plus sigma. So this is the recursion relationship I had. Alright? Is it clear? Alright, now, so this is what we're trying to do, right? I mean, so let's go back to that.
What happened with the z right there before you erased it?
Okay,
The z on the right, that's on the right side of the equation, the z is gone.
no, it should be there. What was here, I mean,
Okay.
there's a z, that's why it
You
was
have
z
z
to the
to the n
minus
plus
1.
sigma
Yeah, n plus sigma minus 1, but
plus 1.
yeah, it was n plus sigma minus, but I removed, we had like this, okay, originally, right? And this is common, which I can write as, if you want, if you didn't want to do it, you can say, I'm comparing the coefficient of z to the power of n plus sigma on both sides, you can do it that way. Okay, but because this is, you can remove, this is a term like that, which is outside the summation, you can pull it out, right? There's a summation here, summation over n. So that can always be pulled out. So what you're doing is comparing the coefficient, so this is what you have, z to the power of n, and then in order to compare the same coefficient to get the recursion relationship, what I have to look at is, this is an infinite series, right? All n equal to m. We want to compare the same power, right? Whether n, this infinite series n 0 to infinity. I want to look at the coefficient of a z to the power m on both sides. Something of that nature. So in order to do that, you have to change this coefficient, right? So that you can have the same power. Otherwise, here it is z to the power n minus 1.
Right, okay, so there was supposed to be a z n minus 1.
Yeah.
And now that extra raising to the power of the n minus 1, is that a mistake now, or is that supposed to be there?
Which one? No, maybe it was,
Okay.
that came because of something else, I don't know what it was. Because,
Okay, okay.
yeah, no, you have something like this, yeah, All you have is z to the power of n and z to the power of n minus 1, okay? And then there was z to the power of sigma also, which we pulled out, okay? I mean, realistic, okay? That term we pulled out. Okay, so we have a very nice expression now. So we go back to this. This is what we're trying to do, right? I mean, now we have so y1. So my first solution would be, I'm going to put sigma equal to 1. Okay, that will be your first solution, right? And then what? We have now these coefficients. We have to estimate that z to the power of 0, right? A1, z1, a2, z squared, blah blah blah. Infinite series is there, and sigma 1 is 1. So I can write that as this is, and then I'm going to pull out a0 because I can calculate only ratios of the recursion, the coefficients, not the actual coefficients, but only ratios I can calculate. Okay, so A1 over A0 is what? We put n equal to 0, then we get that, which is sigma plus 1 over sigma. For sigma equal to 1, it will become 2 over 1, right? It's 2, basically. Sigma equal to sigma 1, right? Now we can start substituting the actual value also. Okay. So this term is really, for this solution, sigma equal to 1, this is 2z, right? Because we are now looking at the first solution. So this one will become, this term is 2z, 1 plus 2z, A0 is here. And we have to get, the next term that we are going to get is n equal to, n equal to 1. N equal to 1 will give me A2 over A1. Sigma plus 2 is sigma plus 1. So this is what we get A2. Which for sigma equal to sigma 1 equal to 1 is 3 over 2, right? But what I want is A2 over A0, so which is nothing but 3. So this will be 3 times z squared. Okay. So the recursion relationship is giving A2 over A1, but what we need for the solution is A2 over A0, because since you know A1 over A0, you can multiply by that and get whatever you want. Okay, so you need to, so here it's A2 over A0. So but what we get from here is that. Right? So that is your series solution. So what we have is, the first solution is the following. What do we have? I have a z also outside, right? But we should have A0. Let's get rid of A0, we don't need that. This is your solution, right? I have this. Okay, what is this function? Okay, this is your first solution. Okay? Do you get it?
I'm just trying to track where A0, what A0 ended up being.
Yeah, because we have A2 or A1, right? So I want A2 over A1 multiplied by A1 over A0 is A2 over A0. So I got that to be 3 over 2. Okay? And this is that, so that becomes 3. I'm just getting it from here. I'm just substituting for different, this is a case with n equal to 0, right? N equal to 1. I'm just putting different values here. And I got, when I put n equal to 0, I get that relationship. And then I substitute for sigma equal to 1 because that is the, for which I'm trying to calculate. For sigma equal to 1, sigma equal to sigma 1, the first root, that is equal to 1. Okay? And that is that. Right?
Where did we get that A0 is 1?
Which one? This one?
That A0 is 1.
You can put anything. One is just as it's a constant, right? At this point,
Not equal to 0.
huh?
Not equal to 0.
Not equal, that's the only thing, okay? You can put one, that's a sort of, any constant times the solution is going to be a solution. So I can have 1 times the whatever solution, 2 times the solution is going to be, it's all proper the solution. It's not linearly independent, but it's a solution. Now I want to, this was a question you had asked previously in one of the lectures that I want to go back. So look at the, I'm going to say that if you convert this into a function, I can get Transkin method and get the second solution. That's what I want to tell you. But what happens to y2? Well, I just made the statement, if sigma 2 equal to 0, if they differ by an integer, you will not get a second series solution. But let us see that, right? Because there's an example here I mean, that statement that I made, what happens with that sigma equal to 0? The recursion relationship is the same. So n equal to 0, sigma equal to 0, this becomes infinity. Your first term becomes infinity, right? So once a1 over a0 is infinity, all the terms are going to break anyway. I mean, so it does not lead to a second, I mean, it does not lead to a solution using power series method, okay? So this is a case where definitely you need another method to calculate your second solution, okay? So which is possible, now that you know the Wronskian method, it's possible if you can tell me what this function is. The series is a function, okay? What is that series? So when you don't, the easiest way when you don't know anything is go back to binomial theorem, okay, binomial series, whether some power of n or something will lead you to that, okay, at least so we can, from there, we can guess what it is. So we know this, 1 plus, this is a simple binomial theorem, right? Any function of this can be expanded in a series like this. That much we know. But that is not leading to me what it is, because this term is fine. I mean, if I put 2, it'll be 2z, but not, you will not get that term, right? So that's not the function. So I need to play with this. So if I put 1 minus z to the power n, I get, well, 1 minus nz. No problem. But still I have a problem, right? But if I make, let's just see what else we can do. Will this give 1 minus z? I just have to just play with these different combinations, and one of them will lead to something, what we want. 1 minus z to the power, that is that. So this one will give 1 plus nz. Okay. All I've done is change the n, right? Here it will become negative n. Okay. So that is n plus 1, right? I mean, so this becomes n times n plus 1 instead of n minus 6. So this one, 1 plus nz plus n times n plus 1 over 2 factorial times this. Okay, if I put n equal to 2, this becomes 2z, right? And 2 and 2 will this will become 3z squared. So this function is nothing but z, yeah, over 1 minus z squared. Okay, that's what it is. I mean, this is 1 over, this is nothing but 1 minus z to the power negative 2. Okay, that's what it is. Okay. So basically, if you have a series 1 plus something, play with what? I mean, you know this one. From here, play with the sign of z, play with the sign of n, play with the different combination, and one of them will lead to whatever you want. Okay. You could have guessed it, but I just want to say that you just play with it. I could have played with 1 plus z minus n also, right? I mean, whatever. These are the only different combination I have. Okay, we play with that. And because you may come across this kind of thing, you will always have minus n. So that will be more like that, except the negative sign, I think. Minus n. So this is like that, except this is negative sign. Okay. So given an infinite series, if you can get a closed form solution, that would be great, okay? Now that you know this, can you give me the Wronskian, you know what's the Wronskian here, in this case? What was P here? What was that differential equation? I erased it, right? This is the differential equation we're trying to solve. Right. So P of z is 3z over z times z minus 1, and this cancels, so it is 3 over z minus 1, right?
Yeah.
Okay. We'll do side change. Okay, so this is 3 over, I'm going to call z prime minus 1, okay? So what is that? One over z, when you integrate, what is that? Three is a constant, so I can pull it out, right? So natural log of z minus 1, okay? So this is nothing but exponential of negative 3, natural log of z minus 1, okay? And 3 log z is same as log of z cubed, right? So I can write this as, I can write an exponential of minus natural log of z minus 1 whole cubed, okay? Alright. So if you're exponential of log z, it is z. Exponential of negative log z is 1 over z, right? So this whole thing is nothing but 1 over z minus 1 whole cubed. Your Wronskian is that. Alright? Alright. So now that you have the Wronskian, we have this first solution in a closed form. We can calculate the second solution that we started with. So I have that as z over 1 minus z squared. And Wronskian is 1 over z minus 4 cubed. Okay. Alright. And y1 squared is then z prime squared, the variable are changed. And that is 1 minus z squared to the power of 4 in some sense. Okay. Since it's even power, I can write it as z to the power of minus 1 to the power of 4 also, right? Alright, so I'm going to write that as z prime minus 1 to the power of 4, and that will cancel then. There will be only one thing there, divided by z prime squared, dz prime, dz again. Oh, I still have to integrate it, right, yeah, I still have to integrate that. Alright. So that is nothing but 1 over, I have integration going on, and then 1 over z prime minus 1 over z prime square. No, I can integrate that easily. Okay. So the first term is nothing but natural log of z.
Hi, Jackie.
Yes.
We're 15 minutes over.
Okay, this you can do the integration, right? That's I'm done, okay? Yeah. Z to the power minus 2 is what? X power n plus 1 is, so that is, there's a negative sign too, right? I mean, so that's so it becomes plus. That's 1 over z. So that is your, that's your solution. So what we did was basically the Frobenius series, right? And we could, from that we got, we could get only one solution. So use the Wronskian method to get the second solution, because the second part series I showed was breaking down. So it was really complete. I derived the, how the other expression of Wronskian and how to get that expression. So this is one complete methodology you got in your hand now. I mean, you know how to solve second order differential equation now, any second order differential equation now. But we may have other methods also. If you cannot find a closed form expression, I need to give you other methods like derivative method or polynomial method and all. But we cannot immediately start looking at our physics differential equation, the Bessel and all that stuff. So you have the methodology now in hand. Yeah, take it.